So today we're going to be talking about rational equations and inequalities. So we've been talking about rational expressions, which did not have an equal sign. And so today we're going to have rational equations. So there will be an equal sign. And this helps us because it makes it a little bit easier to solve. So typically in a rational equation, there is usually a variable in the denominator, but not always. Because of this, we always need to make sure that we check for restrictions and extraneous solutions when we're solving them. So just kind of make sure you always check that at the end. Okay, so solving. The simplest way to solve a rational equation is to clear the denominators. So when we were working with expressions, remember we could not just get rid of the denominators. We had to get a common denominator. The thing about an equation is I can just get rid of the denominator by multiplying it both sides, because as long as I do something to both sides of an equation, it still stays the same. So we're going to multiply the entire equation by the least common denominator, okay? Excuse me. So let's look at our example over here. We have a 5 over an x minus a 1 over a 3 equals a 1 over an x. So the first thing that we look at is what are our restrictions. So we can see we do have a variable in the denominator. So since there's a variable in the denominator, we're going to set that term or that expression not equal to 0. And then remember, when we're looking for the least common denominator, if there's something in a denominator, then it's part of the least common denominator. So I have an x, so I need an x. I have a 3, I have a 3. And then I already have the x, so I don't need to put another one. So what you can see is that I multiplied both sides of my equation by that least common denominator. So I'm kind of distributing that into both of those terms. So when I multiply the 3x by the 5 over x, we can see, it's kind of hard to see, but you can see that those x's sort of cancel out. So then I'm just left with the 3 times 5. Same thing with the next one. When I do the 3x times the 1 over 3, this time the 3's cancel out, and I'm just left with x times 1. And then over here, the 3x times 1 over x, the x's again cancel out, so I'm just left with 3 times 1. So the beauty of this is once I simplify, I just have a basic equation that I need to solve. So I solve that equation and I find that x is equal to 12. And then the last thing we always do is we make sure that the solution does not contradict one of the restrictions. So x is equal to 12. That does not go against our restriction, so then we would keep that solution. All right, looking at our other examples. So we see that we have our first equation, and we're going to state any restrictions and make sure we check our answers. Now in this equation, we can see that we don't have any variables in the denominator, so there are no restrictions here. No restrictions because there's no variable in the denominator. All right, so then what we want to do is we want to think about what's the least common denominator. Okay, well, I have a 3 and a 9. So when you're thinking about numbers in the least common denominator, you're thinking about like the least common multiple. So when I think about 3 and 9, the least common multiple would be 9. So then I'm going to put parentheses around my whole equation and I'm going to multiply it by 9. So I have 9 times x over 3 plus 9 times 5 is equal to 9 times x over 9. So when we simplify that, we see, well, the 9 doesn't cancel out with the 3, but it does reduce. It would give me 3. No fractions to cancel there. We just simplify. And then here, those 9's will cancel each other out. So I have 3 times x, or 3x, plus 9 times 5 is 45, is equal to x. Now I'm just going to solve it like it's an equation. I'm going to move my 3x because my constant's right there. So I have 45 is equal to negative 2x. And we know we need to get rid of that negative 2 by dividing. So we can't simplify any more than that. It doesn't reduce. So we would just leave it as negative 45 over 2. That would be our solution. There were no restrictions to check it against, so we're all good there. Number 2 is the exact same way. So again, we look at our denominators. There are no variables in the denominator, so that means that there are no restrictions. Okay, now I look and I say, okay, what would my LCD be? Well, I have 3 and I have 5. So I look at the product, or, sometimes it's the product of those numbers. In this case, Yeah, the least common multiple between 3 and 5 is just the product of 3 and 5. So that would be 15. So that's what I'm going to multiply my whole equation by is 15. So then I have 15 times the x over 3 minus 15 times the x plus 2 over 5 is equal to 2 times 15. All right, we can see how they reduce. The 3 and the 15 reduce. I'll have a 5 left to multiply with the x. The 15 and the 5 will also reduce, so I will have a 3. And then that doesn't have a fraction to cancel, so now I'm just going to simplify. So my 3 canceled out, so I just have 5 times x, or 5x. Now, notice that this is a negative 3, and it's outside of a parenthesis. There is no more denominator here, but remember, I have to distribute that negative 3 to both of those terms. So I have negative 3x minus 6 is equal to 2 times 15 is 30. Now we're just going to combine like terms and solve. So I have 2x minus 6 is equal to 30. We add that 6 to both sides. So I have 2x is equal to 36. And then we need to divide both sides by 2. So x is equal to 18. And again, there were no restrictions to try to check our answer against. So that answer is a good answer. All right, moving on to number 3. Now I do see that I have a variable in the denominator, so I do need to take care of that. So my restriction, remember I set whatever's in the denominator not equal to 0. So since it's just x, I don't need to simplify anything. So here's my restriction. And then let's talk about what our least common denominator would be. Well, I have an x, so I need to have an x. Then I have 4 and 12, so I think about what's the least common denominator, the least common least common multiple of 4 and 12, and that would be 12. So 12x, and typically you usually write your coefficient in front of the variable, so that's why I wrote it like that. So we're going to multiply all of this by 12x, so I have 12x times my first fraction minus 12x times my second fraction equals 12x times 1. Okay, we're going to simplify. Now, there's nothing, sorry, I forgot my x there. I was like, wait a minute, something has to cancel. Sorry. So my x's are going to cancel here. So the x's cancel out, and I'm left with 12 times 3. Here, the x is good, but the 12 and the 4 can reduce. So the 4 is going to cancel all the way out, and I'll be left with the 3. So I have minus 3x times 1. And then no fraction. Sorry, I didn't write it down right. I'm sorry, guys. I have the 1 12 times the 12x. So here my 12s are going to cancel out, and I have x. Excuse me for my mistakes. So multiply 36 minus 3x is equal to x. Move my 3x over. 36 is equal to 4x. Divide both sides by 4. X is equal to 9. So again, we check our solution against our restriction. 9 is not 0, so 9 is a good solution. All right, moving on. So again, we see in this case, sometimes you're going to have to factor the denominators. The a minus 1, that's in factored form, but a times a squared minus a, it has a GCF. So I'm going to say that this is if I factor out that a, then I have an a and an a minus 1. Okay, so again, first thing I'm going to do is I'm going to think about my restrictions. So if there is a term with a variable in the denominator, we set it not equal to 0. So I have a not equal to 0. I don't really need to simplify that. And then I have a minus 1 not equal to 0. So a would not be equal to positive 1. Excuse me, I'm making mistakes all over the place. Okay, so those are my restrictions. Not equal to 0, not equal to 1. Now we want to figure out what the LCD is. So our LCD is, remember, it's just like finding a common denominator. If something is in a denominator, then it's got to be part of the least common denominator. So I have an a. I have an a minus 1. So I need an a minus 1. Next fraction, I have an a minus 1, but I already have the a minus 1, so I don't need to include it, and then I don't have a fraction there. So I'm going to multiply all of this by a times a minus 1. So when I'm going to go ahead, I'll write a times a minus 1 times 2 over, and I'm going to write it as its factored form. That's going to be most helpful whenever we're trying to cancel stuff out. Minus, again, a times a minus 1 times 2 over a minus 1 equals a times a minus 1 times 1. All right, now here the a and the a minus 1 cancel, so I'm just left with 2. Okay, here, now this one, just the a minus 1 cancels, so I have to distribute that negative a times the 2, so that's negative 2a. And then over here, there was no fraction, so I just have to simplify. I'm going to go ahead and distribute that a back in. So I have a squared minus a. Now, anytime I see an a squared, I know that I need to set it equal to 0. So I'm going to go ahead and move all my other terms over to this side. So that's 2a minus 2. So I have 0 is equal to a squared plus a minus 2. So remember, I want to see, does this factor? Well, what multiplies to negative 2 and combines to 1? Well, that'll be 2 and negative 1. So this factors to a plus 2, a minus 1. Kind of go over here. So what does that make our solutions? Well, remember, our solutions when we're factoring are always the opposite of what's in our parentheses. So a is equal to negative 2 and a is equal to 1. Okay, so we look and we check our solutions against our restrictions. So my 2 does not conflict, but my a is equal to 1 conflicts with my a is not equal to 1. So that one cannot be a solution because it negates one of my, or goes against one of my restrictions. So then my only answer here is just a is equal to negative 2. All right, moving on to number 5. So again, the first thing that we kind of do is look to simplify all of our denominators. Since t minus 1 and t plus 2 are already as simplified as they can get, I need to factor my denominator over here. So I have a negative 2 and a positive 1. So what multiplies to negative 2 and combines to positive 1? Just a little hint, many times these are the factors of whatever that polynomial is. And I see that that's the case here. It would be 2 and negative 1. So this is t plus 2 and t minus 1. All right, so we'll start with our restrictions. So I have a t minus 1 is not equal to 0. So that means a t could not be equal to 1. If t plus 2 is not equal to 0, it can also not be equal to negative 2. Now remember, the restrictions are found just like it's like we're finding the solutions of the denominator, but not equal to. All right, now the next thing I want to look at is figuring out what my LCD is. Well, I have a t minus 1, so that's got to go part of it. I have a t plus 2, so that's got to be part of it. And then I have a t plus 2, which I already have, so I don't need to do it again. And a t minus 1, which again, I already have, so I don't need to rewrite it twice. So now I'm going to multiply that whole thing by t minus 1 times t plus 2. Okay, so when I look at my first one, I take that t minus 1 times t plus 2 times 1 over t minus 1. Now guys, if you can do this without writing this step out, this is kind of a step that sometimes I will do in my head. So if you can kind of do this step in your head, I'm okay with you just kind of leaving this off. So then I have t minus 1 times t plus 2 times 3 over t minus 1 t plus 2. Okay, now, so here's the thing you have to kind of pay attention to is, if you're trying to do this in your head, you kind of are always trying to think, okay, if this is my least common denominator and I multiply it through, it's going to cancel that t minus 1, and so what's left? Well, I have a t plus 2 times 1, which isn't going to change it. All right, same thing here. In my head or on the paper, I can say, okay, those t plus 2's are going to cancel out there. So what am I left with? A t minus 1. And then over here, everything cancels except that 3, so I leave that 3 in the numerator. So now all I need to do is simplify. I have t plus t is 2t. 2 minus 1 is plus 1 is equal to 3. We can subtract that 1. 2t equals 2 and divide by 2. T is equal to 1. Okay, now we look and say, does this solution contradict either one of the restrictions? Right-ro. T cannot equal 1. So that means we have no solution. Because if our solution goes against the restriction, then there's just not a solution there. All right, looking at our next one. We see that this can factor, so somewhere over to the side, I'm thinking what multiplies, kind of write it really small, what multiplies to positive 10 combines to negative 7. That'd be negative 5 and negative 2. So we have x minus 5 and x minus 2. Now we don't have a denominator there, but we do have one there. So we're going to stop for a second, talk about what our restrictions would be. This one's going to take me a little more space. I'm going to write the restrictions down here. So if I have x minus 5 as a denominator, as one of my factors, then I know that x cannot be equal to 5. I have an x minus 2, so I know that x cannot be equal to 2. This one doesn't have a denominator, and this one does, so I already have that one. These are my restrictions. All right, so now I'm going to take a second and multiply this whole thing through. Oh, sorry, I forgot to write what's the LCD. So our LCD, well, I have an x minus 5, so that's part of it. I have an x minus 2, so that's also part of it. This one does not have a denominator, and then this one has an x minus 5, which I already have. So I'm going to kind of shorthand this. I'm multiplying times this. I'm going to save myself a little step. Okay, so, and again, so I'm going to kind of show a step where I would sort of do this in my head. But again, if doing it in your head does not work, then please just always write out all the products. Okay, so if I look at this denominator, if I look at multiplying through my fraction by this LCD, and I see that it cancels everything out of the denominator, then that means that I have nothing in the numerator besides what was already there. Okay, now this one didn't have anything to cancel out, so that means that 2 is going to have to multiply by both the x minus 5 and the x minus 2. Okay, now I have my equal sign, and I think, okay, if I multiply this by this, those x minus 5's are going to go away. So what would I have left? I would have an x minus 4 and an x minus 2. All right, now I just need to simplify. So I'm going to go ahead and FOIL before I distribute. So first, outer, inner, last. X times x is x squared. Outer is negative 2x. Inner is negative 5x. Last is plus 10 equals another FOIL over here. X times x is x squared. X times negative 2 is negative 2x. Negative 4 times x is negative 4x. Negative 4 times negative 2 is negative 8. All right, I need to do a little simplifying. I'm going to kind of shorthand this. This right here would give me negative 7x, so I can distribute that 2 in. And then here, this would give me negative 6x. So I've got 3 plus, I'm going to distribute that 2 into all of these terms, 2x squared. Now I'm not distributing it to the negative 2x and the negative 5x because I've already simplified that, and that's negative 7x. So that's going to give me negative 14x, and then 2 times the 10 gives me plus 20. And then over here, I have x squared minus 6x. I'm sorry, that should be plus 8. Plus 8. All right, still need to combine all of our like terms, but I do see that I have x squareds here and x squareds here. The coefficient, there's more x squareds over here, so I'm going to move all of this stuff, all the right side, over to the left. So I subtract my x squared, I add my 6x, and I subtract my 8. So subtract my x squared, add my 6x, subtract my 8. So all that's gone over there. Now I am going to combine all the like terms while I can. So 2x squared minus x squared gives me x squared. So I took care of my squareds. Negative 14x plus 6 is a negative 8x. Then I have 20 minus 8, that is 12. And then I have a plus 3, so that's plus 15 is equal to 0. And then I've got to solve and see what does that simplify to. I have multiplies to 15, combines to negative 8. That'd be a negative 5 and a negative 3. So I have x minus 3, x minus 5. So my solutions are 3 and 5. So again, I want to check my solutions against my restrictions. 3 is okay, but 5 is not. So I'm going to cross out my 5. So the only solution here would be x is equal to 3. Okay, let's look at our next page. Now, we're going to be doing some word problems, and I know word problems are not everyone's favorite, but that's okay. We've kind of done some problems like these, so it should look a little bit familiar, but again, you're going to see we've got a few different kind of different aspects of this that's going to make it a little bit different. All right, so uniform motion and work. We've already talked about this, and we've used this formula and done word problems with this previously. When we see distance, we know distance is equal to rate times time, or sometimes you see that distance equals to RT, and so or D equals to R times T. So just kind of shorthand, we'll use that in this. And then we also see that work completed, or like sometimes I'll say the job done, is equal to the rate times the time. Okay, so the rate of work times the amount of time they work equals to the one job done. All right, so just like we did previously, we always set up kind of a, we set up a chart for these problems. Okay, so it says a kayaker spends an afternoon paddling on a river. She travels 3 miles upstream against the current and 3 miles downstream with the current in a total of 4 hours. In the still water, when there's no current, the kayaker can travel an average speed of 2 miles per hour. What is the average speed of the river's current? Okay, if you remember doing these before, we set them up as rate times time is equal to distance. Okay, now you notice that it did give us distance. And then previously, I think we've done these with systems of equations previously. But one of the ways that we're going to do this time, because let's tie it back to what we're working on rational equations. So in every single one of these problems, it's going to give you a rational equation. So here, Moses says, what is the average speed of the river's current? So we're going to be looking for rate, but we're going to be using the formula. This is how we're always going to do these, is we're going to always be talking about time. And to get time by itself, it's distance divided by rate. Okay, so that's going to be important when we're filling out our chart, because really it's going to seem like we don't quite have enough information. All right, so remember when we did the chart, we had like the upstream and the downstream. Before we did rate times time equals distance, but we're going to take the distance as our first column, then the rate, and then the time. Okay, so again, we're going to be dividing distance by rate to equal the time. Well, it told us that she did 3 miles upstream and 3 miles down. So there's our distance, 3 and 3. Now our rate, it did tell us what she's able to kayak, like her speed, whenever she's on her own, like with no water pushing against her. And remember when we talked about these were rate, and it was like with the current meant you added the current, and going against the current you meant you were subtracting it. So we could say that this would be 2 miles was her speed, and we're going upstream, that's against the current, so we'd be subtracting the current, and I use the variable c because that's what we're trying to solve for here. And then going downstream, she has her 2 miles per hour, excuse me, and then we're adding the current speed to it. Okay, now here's what we're going to do. We are going to take the distance divided by the rate, so 3 over 2 minus c, and 3 over 2 plus c, and then we're going to write an equation based on the total number of hours. Okay, so we know that the time upstream plus the time downstream is equal to 4. Okay, so we're going to write that out. So I have 3 over 2 minus c plus 3 over 2 plus c is equal to those 4 hours. All right, so now this looks just like what we just did. We have a rational equation. So we're going to think about, now we will think about what the restrictions are in a second, but more like we'll kind of write them off to the side, but we'll just kind of check them at the end. So our restrictions will be c is not equal to plus or minus 2. All right, so we just got to make sure that our answer doesn't conflict with that. So our LCD here is going to be, I'll write it over here, LCD. I have a 2 minus c, so a 2 minus c is part of the LCD. I have a 2 plus c, so a 2 plus c is part of the LCD. So I'm going to take this whole equation and multiply it by 2 minus c, 2 plus, oops, sorry, I wrote that backwards, 2 plus c. Okay, so again, do whatever works best for you. I tend to not, instead of writing it all out, I kind of tend to like cover up parts. So here, when I say, okay, if I multiply, I'm distributing this whole thing in, and I do a 2 minus c, this times that, the 2 minus c's are going to cancel each other out. So what's left? The 3 and a 2 plus c. So I have 3 times 2 plus c. Okay, that kind of takes care of that fraction. Then over here, I have 2 plus c in the denominator. So that means when I multiply them out, the 2 plus c's are going to go away. And then I'm just going to have the 3 and the 2 minus c. So plus 3 times 2 minus c. And then on the 4, nothing is there to cancel it out, so it gets it all. 2 minus c, 2 plus c. Okay, so let's start simplifying. We're going to distribute our 3's, and over here we need to FOIL. 3 times 2 is 6. 3 times c is plus 3c. 3 times 2 is 6. 3 times negative c is negative 3c. Now, I'm going to go ahead and FOIL before I distribute. Now, I do see that these are like difference of squares factors. So I see that that would just be 2 times 2 would be 4. I see that my outer and my inner, I'm going to have a positive 2c and a negative 2c, so those are going to go away. So I just have a negative c squared left. Then I'm going to combine my like terms over here and distribute that 4. Now I see my 3c and negative 3c just cancel straight out, so I have 12 is equal to 4 times 4 is 16. 4 times negative c squared is negative 4c squared. Now I'm going to move that 16 over. Then I get negative 4 is equal to negative 4c squared. So we need to get rid of that coefficient. So I'm going to divide by negative 4. 1 is equal to c squared. And then we would take square root, square root. Now remember, when we take a square root, we're going to put a plus or minus with it. Now, obviously, if we are talking about rate, we're not really going to have a, well, I guess it kind of does work out because we're adding, adding 1 and subtracting 1. So we can kind of see that our current, the speed of the current is 1 mile per hour. All right, looking at our next one. Now, this is a job problem. So this is going to be, we're going to talk about their rate, like each individual person's rate is going to be their time 1 over the amount of time it takes them to do it together. Okay, remember, we've talked about this before. We've done these word problems. So Jason can leave, we'll write that, sorry, work is equal to rate times time. So Jason can clean a large tank at an aquarium in about 6 hours. Let's do our rate times time is equal to work. So we have Jason. If he can do it in 6 hours, then his rate is 1/6. He can do 1/6 of the job per hour. And then when Jason and Lacey work together, they can clean the tank in about 3.5 hours. About how long would it take Lacey to clean the tank if she works by herself? So we don't know how long it takes Lacey to do the job. So we're going to say it's 1/x. Now, it told us the time. Remember, in these work problems, time is always the time that they work together. So they both work for 3.5 hours together to get the job done. And then we just multiply straight across. So that's going to go in the numerator over 6, and then 3.5 over x. Now, always, 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 when you're doing work problems, you write the amount of work that each person did is equal to the one job done. So this was Jason's work, and this is Lacey's work, and they completed one job. Okay, so then we look and say, okay, what would our restrictions be? Well, our only restriction here is really 0. So Lacey can't work for 0 hours. And then I got to go figure out what my LCD is. Well, I have a 6 in the denominator, so I need a 6 in my LCD. I have an x on the denominator, so I need an x for my LCD. So now I'm going to multiply this whole equation by 6x. Okay, so here again, I'm going to kind of do my little covering up trick so I don't have to write everything out. My 6's would cancel here, so I'm going to have 3.5x plus my x's would cancel here, so I'm going to have, 3.5 times 6. And then here, there's nothing to cancel, so I have 6x. So now when I simplify, I get 3.5x plus 3.5 times 6 is 21 is equal to 6x. I'm going to get all my x's on one side, 3.5x. 21 is equal to 2.5x. And then we divide both sides by 2.5. X is equal to 8.4. Okay, so it would take Lacey, oops, I spelled my name with an E, 8.4 hours alone. Okay, so that's her time alone. All right, now one last thing that we're going to talk about today is solving rational inequalities. Okay, so a lot of the steps here are very similar, but there's a few things that we have to do to kind of make sure we're thinking about everything. So we can solve rational inequalities by applying the wave. Remember, when solving inequalities, there's shading involved and open and closed points. So the first thing that we're going to do is we are going to move everything to one side so that we can make one side equal to 0. Because anytime we use the wave, remember, we're talking about that x-axis, right? So when everything is equal to 0. So when the y value is equal to 0. So that's why it's important to get everything equal to 0. So then we're going to give everything a common denominator so it can be combined into one fraction. Then use our critical points, which remember, those are our zeros and our vertical asymptotes. So we got to think about what about the numerator, what about the denominator, and the leading coefficient to draw our wave. Then we determine, do we want it above? That's when it would be greater than or equal to, or below if it was less than or equal to. And then write your shaded region and interval notation on a number line. All right, so let's look at some examples for this. Now, like I said, the biggest thing that you're going to do is you're going to first make sure that they're equal to 0. And if they're not equal to 0, then you've got to do that first. Okay, so we look and we see that this has an equal to. So this means the points are going to be closed points. And it's greater than, so we're going to shade above. Okay, I like to just kind of think about that right off the bat. Okay, Now, here we need to think, now that it's equal to 0, that one side of the fraction, it's completely simplified. So now we're going to think about what is our 0. And remember, the 0 comes from the numerator. Okay, we set the numerator equal to 0. So x plus 3 is equal to 0. So x is equal to -3. So we have a 0 at -3, 0. And then we have a vertical asymptote. And remember, the vertical asymptote comes from the denominator. So it's what is the denominator? And remember, it's not equal to, but it's like x minus 1 is equal to 0. So x is equal to 1. So remember, we have that vertical asymptote, that line that we can't cross at x is equal to 1. So we look and we say, okay, our leading coefficient is positive. So leading coefficient is positive. So we're going to start above on the right. Okay, and then we have no double roots, so no bouncing. Okay, now remember that when you have zeros, this you'll know whether it's a close point. So your close point is like for your 0, but remember vertical asymptotes are always open points. Okay, because they cannot, they're like the restriction of the solution. So we can't have that as a solution. So that's why we make it an open point. So I see that it's a closed point. So I'm going to give it a closed point for my -3 and an open point for my 1. We said we're going to start at the top right, no bouncing. So we're going to just go straight through them. And then we want greater than, so we're shading above. So there are 2 parts that we're shading above, excuse me. So now what's our interval? Well, it starts all the way over at the left side, so that would be at -infinity and goes to -3. Remember, it's got a closed point, so it needs a bracket, not a parenthesis. And then we have the union of that, and then we start at 1, and it's open, so it needs a parenthesis, and it goes to infinity. All right, looking at the next one. Now we see, okay, first thing we notice that these are going to be open points. And that means it's less than, so we're going to shade below. Now, this one is not equal to 0, so that means we need to move that 1 over. So I have x minus 3 over x plus 1 minus 1. And remember, 1 could be written like 1 over 1 because we want to think about it as a fraction. We need to get a common denominator. Okay, so because with these two, we don't want to multiply through by the least common denominator. When we're doing inequalities, we just are always keeping it equal to 0. Okay, and we need the fraction part of it. So my least common denominator, I have an x plus 1, and then I have a 1. So I don't really need to do anything with that. So that means that this fraction needs to get an x plus 1 in the denominator and an x plus 1 in the numerator. All right, now I see that I have a common denominator. So usually at that point, I write one big fraction, x plus 1. I didn't do anything to change my first fraction, so I'm just going to bring it down. But then notice, this is a negative 1 that's distributing in here. So I have to put the negative. So then I have negative x minus 1 is less than 0. Now, something weird happens in this one. We see that it kind of, the x's cancel out, and I have -4 over x plus 1. So in this case, I don't have a 0, right? Because -4, there's no variable in the numerator. So the 0 is just none. There is none. There's no variable in the numerator. And then I think about my vertical asymptote. Remember, that always has to do with the denominator. So I have x plus 1 is equal to 0. So x is equal to -1. Now we look and we say, hang on a minute, this one, it has a leading coefficient that's negative. So that means we're going to start below on the right. And then again, there's no double roots, so no bouncing. All right, so I only have one thing to put on my graph. We know it's a vertical asymptote, so it has to be open. and it's -1. There's not really a curve here. We're just kind of drawing a line. And then we wanted to know, where is it below the axis? So it's below the axis over here. So our first point is -1. It's open, so it gets a parenthesis, and then we go to infinity. All right, 2 more. So again, first thing, I'm going to look at my inequality symbol and decide, what do I know about it? Okay, I see it's going to have closed points because there's an equal sign. It's greater than, so I know I'm going to shade above. Now again, that first step is getting everything moved to one side. So I have 6 over r minus 5 over 2 is greater than or equal to 0. So now I need to think about what would be my least common denominator. My least common denominator, I have an r and I have a 2. So my least common denominator is a 2r. So this one needs a 2 in the top and a 2 in the bottom. And this one needs an r in the top and an r in the bottom. So I can see both of my denominators at this point are 2r. So I'm going to write it as 1 fraction over 2r. I have 2 times 6 is 12 minus 5r. Now, we typically write things in order with the variable in the front. So I'm going to go ahead and do that because it would mess up our wave if we weren't thinking about it like that. Okay, and then again, this is greater than or equal to 0. All right, now we look right here at our leading coefficient. Our leading coefficient is negative, so we're going to start below. Again, no double roots, so no bouncing. No double roots, so no bounce. Okay, so I look and I think about what's the 0, what's the denominator, what's the vertical asymptote. So -5r plus 12 is equal to 0. So this is for the 0 because it's based on the numerator. We move that 5r over. 12 is equal to 5r. Divide both sides by 5. R is equal to 12 over 5. And then my vertical asymptote is just that denominator. 2r is equal to 0, so r is equal to 0. Now, this should have a closed point. Asymptotes are always open, so open at 0, closed at 12 over 5. We have a negative, so we start below, and then we go up and we go back down. Now, we're looking for when it's shaded above, when it's above the line, so I'm going to shade there. So my interval, we start at an open 0, so that's parentheses 0, and we go to 12 over 5. Oops, sorry, that should be a bracket. My bad. It's a closed point, so it needs a bracket. All right, last example for today. So we look, we see these should be open points. Less than, so we're going to shade below. First thing, move everything to the right. X minus 4 over x is less than 0. Okay, now we see we need to get a common denominator. Remember, this is like it's over 1. So I have a 1 and an x, so my common denominator just needs to be an x. So if I multiply this denominator by x, I have to multiply the numerator by x. So I have x squared minus 4 over x is less than 0. Okay, I see that numerator can factor, so I have x plus 2, x minus 2 over x is less than 0. So our leading coefficient is positive, so we're going to start above with our wave. And no double roots, we can see that there's not anything squared. So my zeros are from the numerator. X plus 2 is equal to 0, and x minus 2 is equal to 0. So x equals -2 and +2. And then my vertical asymptotes, set that denominator equal to 0, so it's just x equals 0. Now I put them on my number line. Now these are all going to be open points because it started as an open point, and the vertical asymptote is always an open point. So I have -2, 0, +2. We start above, we go down, up, down. And then we're looking for below our graph or below our number line. So we have there and there. So we're starting all the way to the left at negative infinity and stopping at -2 open point. So it needs a parenthesis. And then we're starting back at 0 and going to 2, both open points. All right, that's it for today.